Welcome to today's lecture on Command and Data Handling, or CDH subsystem, in my Space Robotics course. By the end of this lecture, you'll be able to define the Command and Data Handling subsystem, or CDH, identify typical requirements and design considerations, and also be able to verify that the design closes, and understand how different technologies are designed for space robot missions. All right, so to begin, CDH stands for Command, Data, and Handling. Let's define what we mean by Command and Data Handling, or CDH, which is often described as the nervous system of a spacecraft. At its core, the CDH subsystem is responsible for interfacing between all other subsystems, which you can see by all of these interconnected arrows, coordinating commands and data across payloads, sensors and actuators, and also enabling autonomy and supporting ground interaction. We can break this down into three essential terms: command, data, and handling. Command answers the question of, what should I do? This refers to the generation, distribution, and execution of commands. The onboard computer, or OBC, seen down here, receives instructions either from ground through the radio or from internal logic, which can be seen in this connection. These commands are then sent to appropriate subsystems or payloads. The OBC is central to all of the subsystems. Data answers the question, what information do I have and how should I store it? CDH is responsible for collecting data from sensors, payloads, and subsystem components, and that includes science data, health and status, and timing information. That data is either processed directly by a payload processor over here, or temporarily stored in mass storage over here, to be transmitted later. Handling answers the question, how should I package and move information? Handling is all about formatting, compressing, prioritizing, and routing information. This includes moving data between subsystems and ensuring it reaches the radio for downlink, or gets passed on to other subsystems for onboard use. Together, these three pillars of command, data, and handling make the CDH subsystem essential for spacecraft autonomy and operations. To take a closer look at the many roles played by command and data handling, we have this flowchart. This diagram breaks down some of the key functions of CDH and shows how different signals are passed between subsystems in support of each role. We'll walk through four main CDH functions: command decoding, mode control, telemetry generation, and fault detection and recovery. But first, command decoding. At the top of the diagram, we see commands from operators entering the communications subsystem. These might be instructions like switch to science mode, point to a new target, or begin data downlink. Those commands are passed on to the onboard computer, or OBC, which acts as a central brain. The OBC decodes those instructions and routes them to the appropriate system. For example, operation commands are then sent to the payload over here, or thrust commands are sent to the attitude control subsystem. Next, we want to talk about mode control. The OBC is also in charge of managing what mode each subsystem is in. That could include telling the electrical power system to enter low power mode or commanding the ADCS to change its orientation mode. You can see this shown through the diagram through the power mode component signal going between the onboard computer and the electrical power system. Onto telemetry generation. This is where the CDH system collects information about the spacecraft's performance and state of health. The OBC receives state of health signals from the electrical power system, timing data from the clock, sensor readings from the attitude determination control system, and science data from the payload subsystem. All of this is stored temporarily in the memory and later routed back to the communication system as telemetry data to transmit to operators. Finally, let's talk about fault detection and recovery. The onboard computer continuously monitors for signs of failure or anomalies across the spacecraft. If something goes wrong, say a component overheats or a system goes unresponsive, the CDH subsystem can take action. That might mean switching to safe mode, rebooting a subsystem, or reducing power draw through the power mode signals we saw earlier. These self-corrective actions are essential for enabling autonomy in space missions. We discussed this more in detail in the flight software lecture, but in this lecture, I want to focus more on the hardware implementation of the CDH subsystem. Just now, we talked about the roles and function of the command and data handling subsystem, but we're going to move now into how we actually implement those roles through hardware. This diagram shows the overall architecture of a CDH system, and we'll focus on 4 key components: the onboard computer, the data bus, mass storage, and the payload processor. Let's begin with the onboard computer, or OBC, right here. This is the central brain of the spacecraft. In the middle, you'll see the central processing unit, or CPU, which executes all flight software and real-time decisions. The CPU connects to read-only memory, or ROM, where firmware and boot instructions are stored, and to random access memory, or RAM, which temporarily holds data during operations. The watchdog timer is a safety feature. If the CPU gets stuck or crashes, the watchdog detects the problem and triggers a system reset, helping the spacecraft recover on its own. All of these components talk to each other via the CPU data bus in orange. This is an internal pathway for moving data quickly between memory, processor, and input-output ports. Next is the spacecraft data bus, shown in pink, that connects the OBC to the rest of the spacecraft, like the attitude control system, the communications subsystem, propulsion power, etc. The bus interface and I/O modules, like the digital input-output and custom analog to digital converters, help translate and transmit data between subsystems. Below the CPU, we have mass storage. This stores telemetry logs, science data, and system events, especially when there is a delay between collection and transmission. It plays a vital role in telemetry generation and data buffering during downlink. And finally, the payload processor, located on the bottom right. This is a small computer dedicated to the spacecraft's scientific instruments. It might process camera images, detect features, or compress data on board, all before sending it to the OBC or then directly to the communication subsystem. So to summarize, the OBC executes commands and coordinates activities, the data bus connects all subsystems, mass storage preserves and organizes mission data, and the payload processor enables onboard autonomy for science. So now that we've covered the architecture and hardware of the CDH system, we need to ask an important question. How do we actually get that hardware to function reliably in space? This slide introduces some of the environmental threats our electronics face in space to consider in your hardware or downstream software design. On the right, we see a major environmental input, particle radiation. Radiation in space includes ionizing and non-ionizing doses, as well as single event effects, or SEEs. The chart shows how particle radiation causes bit flips in memory, changes in current draw, and even voltage instabilities in sensitive electronics like our OBC. Over time, exposure integrates into what's called total ionizing dose, or TID. This leads to long-term degradation of microelectronics, solar cells, and optical components. Then we have single event effects. These are abrupt disruptions caused by a single high-energy particle striking a circuit. They can lead to data corruption, image noise, unexpected reboots, and in severe cases, circuit damage or full system shutdown. To protect against these threats, we face a trade-off. Do we use radiation-hardened components, or do we take the risk with commercial off-the-shelf parts, known as COTS? COTS parts are cheaper and more available, but they're more vulnerable to radiation unless carefully screened or shielded. To build fault-tolerant architectures, we often use a few common strategies. TMR, or triple modular redundancy, which means running 3 processors in parallel and comparing their outputs to some communal vote. If one fails, the system votes and selects the correct results. We also rely heavily on watchdog timers, which we discussed in the previous slide, which reset the processor if the entire onboard computer becomes unresponsive. And we maintain reset mechanisms and safe mode scripts so the spacecraft can recover without human intervention. One of the most critical decisions you'll make in spacecraft design is the selection of your onboard computer. There are several key trade-offs to consider, and we've highlighted them across the top of this slide. First up is power versus performance. On the left, we have NASA's Ingenuity helicopter, which flew on Mars with a Qualcomm Snapdragon 801 processor. This was a consumer-grade CPU designed for smartphones. It was chosen because it was lightweight, low power, and delivers high performance for its size. And that was essential for real-time flight control and image processing, especially within a tight energy budget from its small solar panel. But Ingenuity's processor was not radiation hardened. It relied instead on environmental shielding, redundancy, and a short mission life. Compare that to Perseverance's OBC, which is shown right here. This is a radiation-hardened CPU board developed by BAE Systems using RAD750 processors. These are built to survive harsh radiation environments for long-duration missions. What's the trade-off, you may ask? It is much higher cost, it has a larger form factor, and lower raw performance compared to COTS processors like the Snapdragon. Here, we illustrate a clear example of how trade-off between radiation tolerance and cost, and between simplicity and fault tolerance. Now let's talk about processing type. So far we've seen CPU-based OBCs, but increasingly we see missions using GPUs and FPGAs for specialized workloads. GPUs, like the NVIDIA chip shown here, are excellent for parallel tasks such as image processing or running neural networks. They've flown on missions like FlySat-1, which used a Myriad-2 AI processor to select which images were worth downlinking. They are power hungry and radiation sensitive, but their use is growing in low Earth orbit and short duration missions. FPGAs, or field programmable gate arrays, are a different breed altogether. They allow you to reprogram the hardware logic itself, making them ideal for tasks like custom sensor interfaces, high-speed signal processing, fault-tolerant logic with built-in voting or self-repair, and they're widely used in space avionics today, from CubeSats to flagship missions. They're especially valuable when low latency reconfigurability or rad-hard logic is required. You can think of FPGAs like muscle memory, where there's almost a reflex, whereas CPUs and GPUs have to go to some core processing. Depending on your mission, you should use a CPU when general purpose logic and flexibility are needed, a GPU when you're doing data-heavy or AI-driven tasks, likely for payload processors, and then an FPGA when you need custom, high-speed, or radiation-tolerant hardware control. All right, another design consideration could be about whether you use mass storage or memory and what kind. At a high level, the difference comes down to how data is stored and accessed, and whether or not that data sticks around when the power goes off. We divide these into volatile and non-volatile memory types. Volatile memory, like RAM, or random access memory, only holds onto data while the system is powered on. It's fast and efficient, but all data is lost on reboot or shutdown. Non-volatile memory, on the other hand, like read-only memory, flash, or FRAM, preserves information even when the spacecraft powers down. Let's go through the types shown here. On the far left, we see a traditional hard disk drive, a mechanical device with moving parts and spinning platters. While used on Earth for large storage at low cost, these are rarely used in space due to their power draw, fragility, and poor shock resistance. Right below it is a solid-state drive, or SSD. These are much more common in space, especially in CubeSats. You might recognize this acronym from an SD card that you put in cameras. They use flash memory, which is non-volatile and can hold gigabytes of mission data. They have no moving parts, which improves reliability, but their single event upset, or SEU sensitivity, can be a concern in radiation-rich environments. In the center, we have read-only memory, or ROM, often used to store firmware or bootloaders. It's non-volatile and extremely stable, but cannot be rewritten during the mission. An example on Earth is a CD, but something that is more implemented in space can be seen down here. Next, we have RAM, which you can see a chip here. This is volatile, fast, and used for real-time processing, but it's also highly vulnerable to radiation. Soft errors, where a bit flips from 0 to 1 due to a charged particle, can cause major problems in unprotected RAM. This image over here is a space-rated solution for random access memory. This is from the company Nano Explore, and this kind of memory is built to withstand total ionizing dose, or TID, and recover from bit flips using error-correcting codes. On the far right, we see an instance of non-volatile RAM, a module from the military and aerospace electronics. This represents a balance of capacity, radiation resistance, and reliability, perfect for storing flight logs or science data between ground passes. So to summarize on memory, RAM is fast, volatile, and vulnerable. Flash is versatile but must be carefully screened for radiation. ROM and EEPROM are great for permanent storage, and radiation-hardened memory is essential when your mission needs long life and high fault tolerance. Each choice involves trade-offs between capacity, power, and reliability, which you will explore in this module. There are three main types of data bus architectures to be aware of: linear buses, point-to-point buses, and wireless communication. First, we have the linear bus, which you can see here in the block diagram connecting many subsystems and components together on the right. This is a shared communication line that connects multiple devices in parallel. Each device listens on the same bus and takes turns talking. It's compact and efficient, ideal when you need to connect many subsystems with minimal wiring. An example of that format is the PC104 data bus seen on the top left. This is a modular bus system commonly used in CubeSats. Boards are stacked on top of each other, connected with the same pin headers, forming a linear bus backplane. It's a practical example of a compact shared bus architecture, but it's vulnerable to signal contention and bus failure since all nodes share the same line. Next is the point-to-point bus. This type creates dedicated links between interfaces, one-wire pair connection, seen between this, for example, the high-speed radio and payload data storage, and then this data storage and the payload. Point-to-point is typically faster, more robust, and easier to isolate in case of faults. The trade-off is more cabling and fewer total connections. And finally, there is wireless communication, which you can see here in this diagram. This is still emerging in spacecraft interiors, but it's appealing for reducing cabling and weight. Wireless can simplify integration and allow more flexible architectures, but also introduces electromagnetic interactions, packet loss, and security concerns. Let's now look at how these are applied in real hardware. On the right, we see an image of different types of common communication protocols enabled through data buses. I2C, which is on the top, is a linear bus protocol that uses just two lines. It's simple and space-saving, but fragile and limited to low-speed operations. SPI, or Serial Peripheral Interface, in the middle over there, is a point-to-point protocol that's fast and full duplex, meaning it talks both ways. It's often used for memory and sensors where speed matters. And then UART is a peer-to-peer serial connection used for devices like GPS modules or terminals. It's slower, but very reliable. Also worth noting is the CAN bus, a robust fault-tolerant linear bus that's not shown on the slide, but is quite popular in the automotive industry and now aerospace. SpaceWire is a high-speed, high-reliable point-to-point protocol developed for ESA missions, and Ethernet, which is, yes, something that you use on ground, is increasingly used for payload data or internal spacecraft networking. Each bus comes with trade-offs in speed, where point-to-point is fastest, trade-offs in robustness, where CAN and SpaceWire are ideal, and number of nodes, where linear buses are easier to scale but more prone to shared failures. Now that we've covered CDH hardware and design considerations, let's talk about a critical verification step: building a data budget and profile for your mission. This is where we check, do we have the processing power, memory, and storage needs to support everything our spacecraft wants to do? The first step is to define each component's needs qualitatively in a table like this. We list out the key components of every subsystem, like payloads, sensors, actuators, and radios, and then estimate their demands across several categories. Let's go through the column headers together. Throughput estimation, it tells us how much data a component will generate or consume. High throughput systems like science payloads or transmitters may overwhelm slower buses or storage if not accounted for. CPU utilization estimates how much processing time the component needs. If too many high CPU components are running at once, we may exceed the capacity of the onboard computer. Non-volatile memory refers to long-term storage needs, things like firmware, logs, and saved data. High values here may push you towards larger flash modules or radiation-tolerant SSDs. Volatile processor memory is about RAM. Does the component need to load large data structures into memory? Real-time image processing, for example, often needs a lot of volatile space. And then we look at update frequency. How often does the system need fresh data from the component? Something like a heater might update once every few seconds, but an inertial sensor may need to update hundreds of times per second for attitude control. Related to that is timing accuracy. Is this a component that needs precise time-synchronized measurements? If so, your software architecture and clock distribution must be designed accordingly. The next step in crafting a data budget and profile is to look at the data demands across different mission modes. Now that we've looked at component level needs, let's shift to the second step of CDH verification, evaluating data demands across different mission modes. In this table, each column represents a different operational mode, from initial checkouts to science operations to safe mode, all the way over there. The rows are the same computer characteristics that we talked about in the previous slide, things like throughput, CPU usage, and memory requirements. For example, during science operations, we expect high throughputs, high CPU utilization, and strict timing accuracy. In contrast, safe mode demands are minimal. Low data, low frequency, and low memory usage, because the system is, by design, in a low power recovery-oriented state. To really verify our CDH architecture, we need to go one step further. We need to quantify our data loads in terms of actual kilobytes per second. On the right side, this is a table where we turn these qualitative estimates into real numbers. Each row in this table corresponds to a component in the spacecraft, like the camera, the transmitter, onboard computer, or sensors. Each column is a specific operational mode like before, going from initial startup to, say, data transmission or safe mode. Inside the table, we've quantified how much data each component generates. For example, the camera during science operations generates 775 kilobytes during science operations. That's a huge load that must be buffered and stored if it can't be transmitted immediately. The OBC contributes 48.1 kilobytes per second in every mode based on a reference from its datasheet and internal processing estimates. Other components like the GPS or sun sensor contribute smaller streams, typically between 7 and 11 kilobytes per second. This row at the bottom, the data generated per mode, helps us verify whether our mass storage processor and radio can handle that total load. We fill out this table by going back to each component's datasheet, pulling values for data rate, sample frequency, and packet size, and then multiplying them based on what's active in each mode. To wrap up the verification process, we have to look at how well our mass storage system can keep up with a mission timeline. Even if our processor and data bus are sized correctly, we still need to check, can we store data at the rate that is generated and offload it fast enough before storage fills up? That's what this table and this pair of plots are modeling. These plots are showing 4 orbits worth of operations logged minute by minute for a low Earth orbiter CubeSat. To do this step, this table tracks the generated data in this column, how much we downlink in this column, and then the resulting balance of available mass storage in that column. In nominal mode, we generate about 79 kilobytes per second, which can be seen here. But in data collection mode at minute 19, we generate a burst, 854 kilobytes, which causes a sharp drop in free storage. Downlink starts at minute 21 with 2,250 kilobytes offloaded each minute, which clears out our backlog and restores capacity. By minute 25, we're back in nominal operations and the cycle begins again. Now take a look at this top left plot. You'll see a sawtooth pattern. Storage space, which is on the y-axis, gradually declines and resets during each downlink window. The bottom plot shows generated versus transmitted data and the storage balance, confirming that we never overflow and always recover margin. We also need to think about RAM, your volatile processor memory. Data doesn't go straight to storage or transmission, it's first buffered in RAM. If you're collecting data faster than you can store or transmit, your RAM starts to fill up. And if it fills up completely, you lose the data that is lost in buffer. That's why RAM sizing isn't just about processing, it depends on, for example, this burst rate of your instruments, the latency before writing or downlinking, and how long you need to buffer before outages or transitions. For example, during data collection, we generate 854 kilobytes, which means your RAM must handle at least 14.2 kilobytes per second. And that's just for buffering, not even accounting for computation. So RAM size and data transfer timing go hand in hand. This verification method gives us confidence that we're in the safe zone. But if we weren't, we'd need to either increase storage, buffer less, or transmit more frequently. Let's look at some other verification methods we can use to build further confidence in our CDH system. We'll close out today's lecture with a look at two of the most powerful verification methods we have: software in the loop and hardware in the loop. Let's start with the big picture. At the core of this type of testing, these techniques allow us to validate how our onboard computer and flight software behave, not in isolation, but as a part of a full mission simulation. On the top half of this slide, you see a block diagram. It breaks down the components in a simulated testbed. We simulate the space environment, such as orbit propagation, sun position, magnetic field models, and disturbance torques. And then we model the physics, such as rigid body dynamics, thermal behavior, and so on. This is then passed through sensor and actuator models, and optionally through some interface emulators. And then this entire simulation feeds into the device under test. In this case, it's a satellite processor running the real flight software, but it could be your space robot's processor. The device in test could include algorithms such as ADCS or GNC logic, mode switching, fault detection routines, and more. The difference between software in the loop and hardware in the loop is that software in the loop has an entire simulation of flight software run on a host machine. We verify software logic, algorithm performance, and control timing, and it's great for debugging early without needing hardware. But in hardware in the loop, which is shown here, we add some real components, real processors, real interface boards, and emulators like the ones labeled in this bottom photo. We connect to an engineering model of your spacecraft, in this case a satellite, with actual wiring, power boards, panel emulators, and radio interfaces. This allows us to verify the actual hardware behavior, such as power draw, timing delays, input-output handling, and then how it all reacts to real-world electrical signals. From a compute resource perspective, this is also where you push your system or exercise your system. If your OBC isn't fast enough, can't handle real-time sensor updates or bottlenecks under software load, you will see that here in either the software in the loop or hardware in the loop testing. If I could give advice about when to use either, software in the loop is perfect for verifying software correctness and function performance. Hardware in the loop adds that hardware layer to verify timing, input-output, power, and real-world robustness. Together, they give us confidence that what we launch will work in space. By the end of this lecture, I hope that you are now able to define the function, design considerations, and verification methods of the command and data handling subsystem. We've now seen how CDH integrates across subsystems and the technologies and processes that ensure it performs reliably in space. Thanks for joining me in this course, and I can't wait to see your space robots design.